So basically you have data points xi, yi, which you want to fit to some equation. Call it linear, y is equal to a plus bx or b1 plus b2x. Your data points, n data points. How do you formulate this as a problem in matrix algebra, effectively? Right? That's the aim of the game. So this same set of equations can be written in matrix form in the following way. The y1 through yn are the data points, and x1 through xn. And if you simply multiply these two equations out, you will see that y1, I mean this basically says that y1 is b1 plus x1x, sorry, b1 plus b2x1, y2 is b1 plus b2x2, and so on and so forth. And epsilons are the errors. Okay, so what's the aim in curve fitting? What do you want, what is unknown here? Okay, so you want to try to find b1 and b2. So you have two unknowns, and how many equations do you have? So you have n equations, the little n which you can't see very clearly, but that's the little n. And so this is a problem with m equal to 2 and n equal to, well, n. Okay, so what about the epsilons? If you think that the scatter from, so if you simply plot it and if you find that it fits perfectly smoothly on a straight line, find a slope with 2 points, and if all the other points exactly numerically fit on that straight line, then the epsilons don't exist, you don't have a problem, so to say, right? The main problem will be that if you take any two data points, you can fit a line, and you can keep doing it for all of them, and you will get multiple slopes and intercepts. So that's the over-determined system, right? So, so the epsilons then, if you think that they are errors, that is, you would like to fit the data to a straight line, and these are just small deviations. So you forget about the epsilons. So the idea is that you basically try to fit this equation without the epsilon, and there will be deviations from it which will be the epsilon. So you find the best fitting curve in the sense that Varun has been explaining for last 2 lectures, and all the points will not fit exactly, and then those will be the epsilon that you will find out. So here is the next, so I guess before I go to the solution, since this question came up, right? Okay, so there is, so sorry, I'm jumping because I guess the question came up. So there is, once you fit your data, then you can look at what is the residual vector, which is r equal to y minus y hat. Y hat is the fitted data, and that will again be a vector of length n. And for example, you can look at SAC, the sum of squared errors, or basically the norm of the vector epsilon, and that will be that will okay. And then there is something about okay, and maybe I should talk about, okay, I don't want to talk about this right now. So yeah, so just referring to the epsilons. What would you do if you want to do it for higher order curves? Oh, by the way, I guess I didn't quite say. So this is the problem. The y's are given, the x values are given. What do you need to find? The b1, b2, and epsilons are gone from the equation. And so how do you solve this? So under what category does this fit? Oh, sorry? Maximum what? So this one should have maximum rank, which basically will mean it should be 2. So what's the requirement that it has rank 2? Okay, so it's the same thing that it basically, this is exactly what he was talking about in the problem for this moving, I mean, this is then the velocity, this is the initial condition, and this is the time, if you want to interpret in that language. Yeah? Okay, so how do you solve this problem? You want to find B1 and B2. What's the solution? So you have the solution in the lecture notes. So if you remember it, tell me. Otherwise, look up the lecture notes and. Okay, so I won't give you the solution. You know it. It's in your lecture notes. So it's up to you to find it. Yeah? And. So I guess maybe I should cover this up before I reveal this. Okay, so in the notation of the lecture in the morning, what's this quantity, what's this quantity, what's this quantity? Z, H, X. Okay, so now you know the solution, right? Because this is Z equal to HX and you want to find H, X. Okay, it's switch, I mean, it's, okay. So, right, that's the generalized inverse solution. X transpose X, oh sorry, the matrix that's mentioned.
H is X.
The H is, yeah, the H is X, the Y, the Z, yeah.
Z is Y.
Z is Y and beta is X, and okay, so we can do the translation. Translate from Varahan to Apte, and then, okay, so there. So that's a least square solution. Or generalized inverse solution, X transpose X inverse X transpose Y, that's beta. How about if you want to do this for higher order curves? So if you want to instead of fitting a straight line, you want to fit a 6th order polynomial, what would you do? So we'll have how many unknown parameters, sorry? So if you want to have 6th order polynomial, then you have 7, okay, there is a consensus, good. In mathematics, having consensus is a good thing. That means there is only one true theorem. Okay, so that's what this is, right? You have higher order polynomials, you want B1 through BP for a P minus 1th order polynomial, which again you can write in terms of a equation of exactly the same form, y equal to x beta, where now x becomes the coefficients of, the beta becomes the coefficients of the polynomial, and the x matrix becomes this. Yeah? Question? Oh, I guess I can zoom it, right? Technology. Okay, good. So, let me show this once more. So I think you may want to take notes because this is what you are going to work on. If you remember all of this, good, perfect. But so that's the first one. X, y equal to x beta. X is this matrix here, this one, and beta is that vector here. If you want to do it for higher order curves, the equation remains the same, y equal to x beta, simply that x becomes this one, yeah? Okay, do you see? So if you don't see that this is true, write it out, and that's part of the tutorial, right? I'm not going to write down the steps, so you have to work through this. So if you don't see that the P minus 1th order curve fitting reduces to no lights solution is that it reduces to the form that y is equal to x beta, where now beta is B1, B2 all the way up to BP, and y are your data points, which are y1, y2 up to yn, and x is what is there. So what's the dimension here? N by 1. It better be n by something. So n by p, and this is p cross 1. So there is a little bit of translation between what the number, the notation he had and the notation I have here, but that I think should be straightforward. And then you just have to find the solution which is exactly the same form.
Can I make one comment?
Yes, please.
though in the second case, I would like to consider two things. The first model, the model equation is linear. The second equation, the model is a nonlinear polynomial. Even though the model is a nonlinear polynomial, the unknowns are the coefficients. So it's a linear in the coefficients. So I want to make that.
Okay, yeah, good point. Thanks. Yeah. So I have. So that's the solution. That's a generalized, the one that's not blocked, the equation that's not blocked. That's a generalized solution. X transpose X beta equal to X transpose Y, as long as X is full rank. Full being what will be the rank? In this notation, P. Minimum of NP, but I'm taking the case, okay, so fine. So I should say that you want to fit a pth order polynomial, P minus 1th order polynomial to n points, so n greater equal P, and then, okay, so, n greater than P. And so then you want to find it. How do you find it? So this is where one of the decomposition that he said, there are lots of decomposition, so let me just mention QR decomposition. What it does is, actually I have it here, right here. Okay, so there. So the QR decomposition takes any matrix, a m by n matrix. So this goes back to the m by n again. Sorry. Anyway, so this is a n cross n matrix and decomposes it in form Q and R, where think of the columns of Q are the orthogonalized versions of the columns of A. So what equation would Q transpose satisfy? Either Q, the product of Q transpose or Q transpose Q will be identity. Which one? And solving this. And, I guess it's here. Okay. Okay. So how does QR decompose? How does the decomposition of this form help in solving that equation? So maybe I'm preempting part of what you are going to say, but I guess that's it. Okay, good. Okay, so I thought this was useful for the tutorial, so I'm doing it. And then, yeah. So yes, I'm giving the form. Yeah, exactly. So yes. Okay, fine. So yeah, the aim of the tutorial. Yeah. No. So question answers is a good idea. Okay. So good idea. Yeah. Maybe we can list the questions at the beginning, and we can sort of say veto which ones are more important and answer them.
But I don't want to tell that your question is more important.
No. Okay. So now I mean, sorry, I didn't mean important in the sense of the ones which are. Okay. So basically, if you now substitute this QR decomposition into this equation of the matrix X, so you have this matrix X, and suppose you can do this QR decomposition, and then you substitute here, and then you just sort of say look at the step by step. So QR transpose QR, R transpose Q, which is identity, which is what one of the things was, and then that remains this, and then right, and from here. Basically you come to the equation that looks like this, right? And why is this useful? So one way to do it is, you have this equation, right? And you have this top equation, the first equation, the very first equation. You could just simply find X, do X transpose X, find its inverse, right multiply, and so on and so forth. Why is this equation, the bottom one, better than the top one? Okay, so this goes into algorithms which I won't talk about. Sorry. So R is the upper triangular matrix. What's the inverse? Okay, so okay, I'm not giving you any answers here at all. Zero answers. So these are all the questions that you should think about. That's all. Right? And okay, so what's the whole setup? How do you actually do curve fitting using matrix algebra? So here is the algorithm, which is what you will do in the tutorial. That's your homework. I mean, that's your tutorial, right? So that's what you should do. So you're reading these vectors, which is for those data. So, and this will be basically for this data set, the CO2.dat. So if you see these two, these are matrices. So this is just a data set where the first column will be, actually I forgot which way it's written. If you see, it's clear. It's a CO2 data set, year versus CO2 levels. So the year is X and the CO2 level is Y. So figure out, I forgot which one is which, yeah?
49%.
Yeah, so it's 40, so it's 49. So N is 49. And it has two columns. The one column, the independent variable column is X, which is the year, and the dependent variable Y, which is the CO2 level. And you will easily figure out which one is which, yeah, in that data set. So for that data set, so that's easy to do. Depending on the level of curve you want to fit, you want to formulate a matrix X. If you want to fit a cube, sure. And so then that forms the matrix X. You do the QR decomposition of X by simply the command QR. Okay, very easy, right? So Q comma R equal to QR. And so if you have trouble with these things, I was trying to connect my laptop, which somehow didn't do. So Q comma R, put parentheses, and if you have questions, then we can discuss these MATLAB questions in this, right? So QR is a command in MATLAB that gives you the Q and the R matrices. So you should check that R is upper triangular. Actually, maybe MATLAB does it lower or upper. I forget which one it does. So you can do it upper or lower, and I don't remember. Upper. Okay. So okay, so you should check, right? These things you should check whether R is upper triangular or not. Whether Q satisfies that thing, Q transpose Q equal to 1 or Q transpose equal to 1, right? And identity, I mean, by 1. And then define Z, which is this, and then you have to solve this linear system, and I leave it to you to how to solve this, right? So you decide what's the efficient way of solving this system. It's up to you. You can come up with many different solutions if you want. So okay. Yeah, I guess if you devise 2 or 3 different methods, they better give the same solution. Yes, that's a basic check. Yeah. So have you all understood the algorithm?
How many of you know forward elimination backward substitution?
How many of you have done it in practice by hand, so to say? Okay, so yeah, that's one. And anyway, so you can. So if you get confused, write this down. So what are the dimensions? Okay, so dimension? Okay, so think about dimensions and think of writing the smallest possible dimension, right? So maybe you write it for a 2 by 3 case, and then you will see what that means, right? So R is an upper triangular matrix. R is an upper triangular n cross n matrix. Beta was actually in this case it will be a P cross P matrix. Beta is P cross 1. So you will get so Z better be a P cross 1. So how do you solve a P cross 1? I mean, right? So try to solve a 3 by 3 system where R is upper triangular, and then you will immediately see what to do. Yeah? Or do a 2 by 2 system where R is upper triangular, and then everything else follows. Yes. Oh, how do you read that into the day? So okay, that's MATLAB command, which is load. Thank you. Load in quotes, single quotes, the data file equal to some variable. You may want to call it, say, I don't know, A or something, and this will now, you can put a semicolon after that, and this will be a matrix of 49 by 2, and then you can extract the first column and the second column. So, yeah, okay. Yeah. Yes, please.
Here given as 1949, 19.
Yes. Yes. So.
That could be trouble for you.
Yep, exactly. So okay. Yeah.
You've got a matrix where one column CO2 level. What is the units of CO2 level? And very low. These numbers are in thousands. So you are dealing with matrices where certain numbers are in thousands, certain numbers are in few decimals. You are dealing with You are dealing with elephants and ants. The elephant is going to smack the ants like people. So numerically, you need to think about that.
Yeah. So I was actually going to leave it to them to.
You can throw all your zeros out and then say 1, 2, 3. And then you can have a table. 1 represents 1972. 2 represents 1973. And then
Yeah, no, I think that's
something you need to think about. Why? If you don't do that, the big guy will steal the show. So that's where the numerical problem comes.
So just 1 second, one more thing I wanted to give you, which I thought was there. Oh yes, it is there. Okay, so one more data set. It's a data set, right? So here, another data set is so there are four files in that. So I was just looking up that. It's a JPEG file, but we'll think of that as a data set. Okay, so what do I want you to do with these other three data sets? Yeah.
So they are going to be given all the 3 at one time?
No. So I mean the same operation effectively on all 3, the same sets of operations. The answer here is known. The answer here is not known. So that's a dog, and I want you to figure out what's the top 2. So okay. So where is that? Okay. Okay, so how many of you know how to read images into okay, so the next decomposition of matrices is called SVD. So I will just tell you what it does. Oh, maybe actually, yeah, I could just use this same things there. Okay, so a SVD factorization. I mean, I'm just throwing things at you, right? I'm not telling you what good they are for, but so any M cross N matrix can be decomposed into USV transpose, where S is diagonal. That's what this says. It's a N cross N matrix which is diagonal. U is okay. So again, so U and V are such that the column and the row spaces of them are orthonormal actually. So the columns of U are orthonormal. Actually, V is both row and column orthonormal. So this one is column orthonormal, and this one is orthonormal matrix. So what does that mean? That means that what is a orthonormal matrix? So V transpose V is identity, as is V transpose. But for U, it's not both ways. It's only one way, which is U transpose U is identity. So SVD decomposition is A is USV, where S is diagonal, of course invertible, not necessarily. Okay, so diagonal, that means it's ortho. So S is so let me put it this way. S is diagonal, V is such that VV transpose and V transpose V are identity, and U is such that U transpose U is identity. Yeah. For example, this helps in finding the product A transpose A, because if you do A transpose A, that is simply, well, it's U S V transpose and so on and so forth. U transpose U is identity, which is what I said. So it simply becomes V S square V transpose, and V transpose is V inverse because V transpose equal to identity, and so it helps you. For example, I mean, now you can see where this could be useful, right? For example, you are transpose times the matrix. Okay. The idea is the following. Now you have it turns out that the rank of A is part of S effectively, in the sense that if A is full rank, all the diagonal elements will be non-zero, and if A is rank deficient, then that means, so if A is okay, you can count. That means number of singular values will be 0. I guess this is n cross n. So if A is rank k, then n minus k of singular values will be 0, right? And so what you can do now is with a given matrix which is m cross n, you may not want to deal with this whole. I mean, these are so if both m and n or one of them is large, these matrices are large, U, S, and V. So you may not want to deal with such large matrices. Oh, thank you. And in order to not to deal with large matrices, in many cases it so turns out that many of these SS are close to 0, even if it's full rank, even if it's not equal to 0, many of these SS could be close to 0, and then you could consider them to be 0, right? And then you could simply deal with smaller matrices, because if you have zeros, then that block, so think of writing this as, so let me take, so this is, okay, so this is n cross n, V is n cross n, and let me take the case of, I don't know, m cross n like this, right? And if you have, so this is diagonal, and if say last 10 members are 0, then this 10 by 10 matrix here is basically just 0 matrix. And you only have, so this is already 0 matrix, this is a 0 matrix, if you can see it, which you can't, I guess. This is gone. And so you have 3 0 matrices of appropriate size here, and you only have a non-zero diagonal matrix, let me just call it D here. So this is the n minus 10 cross n minus 10 diagonal matrix. So if you want to multiply this large n cross n cross n cross n cross n cross n matrix with zeros all over, you don't need to consider the whole thing, right? Multiply this with this, what do you get? You get lots of zeros. So figure out which zeros you get, which columns or which rows you need to keep, the others you can simply throw away. So the ones which you know will give you 0, you don't need to store them in MATLAB or in your program. You just throw them away. So let me think for a minute. So let's just do this, right? So D times this, this is, so let me call this K cross K, and this is L cross L, such that L plus K equal to N. So I can multiply this matrix by the block here and plus this. So I can divide this matrix into A, B, C, E. D is taken up of appropriate sizes, and this matrix that I get, the product of these two will be DA times 0C, DB times 0E, and then I'll get 0 and 0. Right? So in this product, C and E do not appear at all. So I don't need to store the rows of this matrix at all. And you can do a similar thing on this side. You don't need to store a part of the columns of U at all. So this is called when you throw away, when some part of this matrix is 0, or you set it to 0. What you can do is, there are small values sitting here. You can set them equal to 0 by hand in MATLAB, for example. And this then, when you set such things to 0, this is called a low rank approximation. And then the advantage of low rank approximations is that you don't need to store certain parts of these large matrices. You only need to store these two, and in this case you will need to store only the stuff that goes here and the stuff that goes here. You don't need so these ones can be taken out and these ones can be taken out. Only you need to store these. So you need to store much smaller matrices. If you decide that I will call everything less than 0.1 at 0. That's a good approximation actually in many cases. So 0.1 is 0. So Okay, so the idea is the following. We want to think of the image as, so what's the image? It's pixels, gray value of pixels, right? So this is a black and white dog. So think of each of them as a real number, as a matrix of some 256 by 300 something. And so these are just, it's a matrix, so that's the matrix A here. The dog is the matrix A. If you can do a singular value decomposition of this, and the dog is equally well represented by U, S and V, because you simply multiply U, S and V, you get the dog back. But you can do better. If you don't want to store the whole thing, all you do is to store things which are small, which are large enough. Say, choose a threshold. Choose, say, 0.1, as I said. Keep only the values of S which are greater than 0.1, and all of them set to equal to 0. Then you don't need to store these columns, these columns and these rows, and multiply those matrices out. It will be an approximation to the dog, right? And see how good you can see the dog. Well, that's actually image compression algorithm, basically. I don't know, that's not the JPEG algorithm. JPEG is more complicated, but anyway. So that's the exercise here, right? So you want to read the dog in as a matrix. How do you do that? Anybody knows? ImRead. So it's a command called imread. File name dog.jpg, and don't forget the semicolon, because if you don't give it, so when you don't give a semicolon, you see the output of the command. What this does is reads the image as a matrix, and if you don't give it, then you will see a 300 by 200 matrix scroll by your screen, which will take a long time. So you set this equal to, say, x, or, well, keeping up with my notation, set this equal to, say, a. Oh, sorry? Oh, it just reads it as a pixel by pixel value, right? I mean, what is the image? When you see an image, what do you see? You need to tell the monitor that the intensity at this point is that much. So that's how it is stored. So it is stored as the values. So, two more. So one more. Unfortunately, this is a. Let me see. The dog is 200 by 300. I don't know if it is, but something like that. So unfortunately, the matrix A will be 200 by 300 by 3. It has for 3 colors. This is black and white dog, so all the 3 colors are actually identical. And so you just need the first layer. So you can say that, let's say, I don't know, B or something is equal to A colon 1. And that's a matrix that you want to eventually deal with, which will be 200 by 300. Yeah? You don't want all the 3 layers, so they're identical basically. Yeah, RGB. Yeah. So those are the. Yeah. It reads it automatically as a color picture instead of reading as. And this happens to be black and white. So. Okay. So now you take your matrix. You do SVD. How do you do SVD in MATLAB? SVD. That's how you do it. Okay. So it's SVD of B. On the left hand side, you can actually put in U, comma V, space, yes, thank you. So U space S space V, and this will give you the matrices U, S and V. The only trick is if M is less than N or M is greater than N, the MATLAB SVD does it in a specific way. I keep forgetting it and I don't want to remember, in fact, so it doesn't matter, yeah. So.
Is there any MATLAB command you're not sure about? You can type help in the name of the command and it will give you the syntax and the example. It's very useful.
Oh, actually, yeah, MATLAB help is quite useful, actually helpful. Not like the Unix man pages, but so yeah. So you can just look for help. I mean, depending on whether B is 200 by 300 or 300 by 200, you will get, so to say, slightly different results. I mean, they swap the columns and rows, and that's all. So yeah. And then the idea will be you want to you want, okay. So rank. So if you set k of these to 0 and L of these to you keep the L of these as non-zero, this one is called the rank L approximation. Right? So you have kept only the L values as non-zero, and so I would like you to do a rank 1 approximation, that is keep only the highest one as non-zero, set everything else to 0, and see what you get. So you will. So what am I suggesting? You do the SVD, you get this. Now you do a say S modified as everything set to 0 except L values as the same as this. So there are many ways to do it. You figure. So one way to do it is to say that S for I is equal to L plus 1 to n if S is n cross n, then I equal to n cross S mod I comma I is equal to 0. Oh, before that you set, so you say S mod equal to S first. So you set this matrix equal to that. So there will be identical matrices, and then you set for all I greater than L, S I comma I equal to 0, and so you are setting all those things to 0. So that's your modified S matrix, and you can get, for example, a B mod by simply again doing so. What should be equal to? B should be equal to U times S times V transpose. So the B mod, the low rank approximation of B, will be U times S times V transpose. Yeah? Sorry? So you can just do U S, S mod, I mean, yes. V transpose, so U S mod V transpose. Of course, the main aim of setting these to 0 is to make sure that you can deal with smaller matrices, which means you can form from this U a U mod which is only these columns, and from this V only the ones which are there. But so if you want, you can do that as well, but because they are 0, you know the answer is going to be the same anyway, so it's up to you. Yeah, and so this will be a rank L approximation to, so B mod then will be a rank L approximation to B, and you want to see the dog out of B mod, right? The modified dog. How do you see the modified dog? You plot, you again make an image out of it, which is I keep forgetting these commands. How do you plot a matrix as an image? I don't remember now. Okay, can I? Yeah. So actually, that one is kind of non-trivial. So maybe I will put this on the. I will put it under. Under the same directory, another file called tutorial.pdf, which will have instructions to form an image out of a matrix, and then you can just see it. Yeah? Sorry? I am sure B mod does it?
Yeah, that's
okay, good. So, or ask the MATLAB expert here how to do all these things instead of looking at the instructions. Yeah. So that's it. And then okay. So that's one exercise. So I told you this is a dog, so you can see the dog, and then you can see how it, so to say, what are the low rank approximations to a dog, and that's actually Eric Kostelich's dog. He took the photo and then put it up on the web and so on. And I want you to do the same thing for this. So these are already matrices. Just save them. When you read them, just load them using. You don't need to do now imread because it's just a text data file. So you can just use load and do the low rank. And I would really suggest maybe try to do the low rank approximations first. That is, don't show the image first. Just do a rank 1, rank 2, rank 10, rank 20 approximation, and see if you can guess what these two are. Okay, and then you can see what it is supposed to be. So, okay, so I think that's So now we'll disperse, or you can stay here if you want, and you can start working on curve fitting and these two. Okay. The curve fitting algorithm. Yes. Yeah. I will. We can reconvene at 5 o'clock, 5 to 5:15. By then, you should have at least tried, if not all of these things, some of these things, and you should have some idea of how these things work. Yeah. So that's a part of hands-on, and I will randomly choose. I will take a sample and ask you to tell me what you did. So.
And we can meet for how long? 45 minutes?
Yeah, 45. I mean, so.
Meet for 45 minutes, answer questions.
Yeah, so 5 or 5:15 we can meet and then answer questions and ask you to ask us questions about the hands-on as well. And yeah, so.
As well as theoretical questions.
As well as, yeah.
Any questions?
So yeah,
And
sure.
the only thing you can do wrong is just not doing anything.
Yes, exactly, yeah.
And as long as you're trying it.
It's going to work. And if it doesn't work, that means that's okay. Ask us questions. I mean, you can ask questions even before, right? So if you get stuck somewhere, please, I'll be around. I'll be in my office or here, or in the library at the most. I'm not sure. I don't think I'll go to the library. So.
Can I fill a Chinese problem? I'm going to add to my problem.
Yeah.
But sometimes I'm not sure, I don't remember the cases, but sometimes MATLAB isn't smart enough to do it on its own, and you have to tell it it's actually
reshape.
matrix, yeah.
No, but I tried.
And it worked,
This worked.
okay.
Yeah. Oh, sorry. There's one thing that does not work. If you do imread, it rates it as it scales it from 0 to 256 integers as integer type and not double type. Comment MATLAB questions, which I'm sure there will be plenty. Please come and ask me if I can answer it, or him, or ask around and so on. In particular, when you do imread, A is read. I just remembered. This is read as an integer matrix, and you need to convert it to doubles to do SVD and so on and so forth. And the command for that is simply double. It's of doubles on which you can do SVD. If you pass on a matrix which is integers to SVD, it complains for some reason. Sorry, I didn't understand. I can't hear you. Sorry. So just try. Squeeze or reshape.
Yeah, we should see.
Yeah.
Well, like, the same thing.
Same thing. So okay. So I think all of you really should try it. And we take help from each other. Take help from anybody you want. But do it. Yeah. Sorry. What do you mean?